The study of road traffic is a multidisciplinary field that combines elements of transportation engineering, physics, mathematics, computer science, and psychology to understand and model the movement of vehicles on roads. One of the most fundamental aspects of traffic flow theory is the car-following model, which describes how vehicles interact with one another in a traffic stream, particularly when they are following each other. The study of road traffic began in earnest during the early 20th century as automobile usage increased and congestion became a significant issue in urban areas. Early efforts focused on understanding traffic flow patterns, capacity, and safety. The first formal models of traffic flow emerged in the 1930s and 1940s, with researchers like Bruce Greenshields laying the groundwork for macroscopic traffic flow theory. However, it was not until the 1950s and 1960s that car-following models gained prominence. These models were developed to capture the microscopic interactions between individual vehicles, providing insights into how drivers adjust their speed and spacing based on the behavior of the vehicle ahead. What are car-following models? Car-following models are mathematical representations of the dynamic interactions between consecutive vehicles in a single lane of traffic. These models focus on how a follower vehicle adjusts its acceleration or deceleration in response to the motion of a leader vehicle. Key variables in these models include headway, distance, the distance between the front of the follower vehicle and the rear of the leader vehicle. Speed difference, the relative velocity between the follower and leader vehicles. Acceleration/deceleration, how the follower adjusts its speed over time. Car-following models are essential for understanding traffic phenomena such as stop-and-go waves, shock waves, and congestion propagation. They also play a critical role in designing intelligent transportation systems, ITS, autonomous driving algorithms, and traffic simulation tools. Some of influential car-following models are shown in this slide. Each model offers a different perspective on how drivers adjust their behavior based on the vehicle ahead. Newell's model. Also known as the time-space translation model, Newell's model is exceptionally simple. It assumes that each vehicle's trajectory is essentially a time-delayed and spatially shifted copy of the leader's trajectory. General Motors and the Gazis-Hermann-Rothery (GHR) models. Developed in the 1950s and 1960s, these models assume that a driver's acceleration is influenced by the speed difference relative to the vehicle ahead and is modulated by the spacing between vehicles. Optimal Velocity Model, OVM. In the OVM, each driver adjusts their acceleration based on the difference between their current speed and an optimal speed that depends on the headway, distance to the vehicle ahead. Intelligent Driver Model, IDM. The IDM is a widely used nonlinear car-following model that blends desired speed, safe distance, and acceleration capabilities. It is known for its realistic simulation of both free flow and congested traffic. The simulation introduced the basic concepts and equations behind car-following models. Demonstrate these concepts through a simulation showing how a disturbance, shock wave, propagates along a line of cars. Here are some of the variables used in the simulation. Position of car I at time t, velocity of car I, acceleration of car I, gap between car 3 and its leader, with LL as the car length, safe gap, a desired distance, buffer, that drivers maintain for safety. Each car adjusts its speed based on the gap and relative speed to the car in front. The rest of the formula used in the simulation are illustrated in the next slide. From the simulation we can make the following observation. Leader car dynamics. The leader, red car, follows a prescribed periodic cycle. Deceleration phase, gradually slows down to a near stop. Stop phase, remains stopped for a short period. Acceleration phase, quickly accelerates back to cruising speed. This creates a disturbance that propagates backward through the following cars. Following car behavior, each following, blue, Car uses the above equation to compute its acceleration, adjusts speed based on the difference in speed and spacing from the car ahead. What do the graphs tell us? Speed graph. Red curve shows the periodic behavior of the leader. Green curve illustrates how the car directly behind the leader responds. Blue curve represents the average behavior of all following vehicles. Acceleration graph highlights how quickly vehicles adjust their speed in response to the leader's changes. Finally, we can conclude this video with these summaries. Car following models are essential for understanding and predicting traffic flow. The simulation demonstrates how a simple proportional control model can reproduce realistic traffic shock waves.